Can we manipulate and control light at the quantum level? Well, to answer this, we must first understand what it means. To answer that, we need to go back to the early 20th century when physicists discovered that light has both wave and particle properties. Light can be described as a stream of photons, which are the smallest units of light. Photons can behave in strange ways that defy our classical intuition. For example, they can interfere with each other, creating patterns of bright and dark spots. They can also be entangled, meaning that their quantum states are linked even when they are far apart. Quantum light is light that exhibits these quantum features, such as low noise, coherence, and entanglement. Quantum light can enable new applications in quantum information science and technology, such as quantum communication, cryptography, computation, metrology, and imaging. Quantum light can also help us test fundamental physics, such as quantum mechanics and relativity. However, generating and manipulating quantum light is not easy. Unlike classical light sources, such as lasers or LEDs, quantum light sources are often inefficient, unstable, or incompatible with each other. Moreover, quantum light is very sensitive to noise and loss in the environment, which can degrade its quantum properties. To overcome these challenges, scientists have been developing new methods and devices to manipulate and control quantum light at different levels, from single photons to many photons, from single modes to multiple modes, from discrete variables to continuous variables. Before we move on to the different techniques to do this, please like and subscribe if you find this stuff interesting so the video spreads to more people that find this interesting. One of the most basic operations on quantum light is to create single photons on demand. Single photons are essential for many quantum protocols, such as quantum key distribution or linear optical quantum computing. However, most of the existing single photon sources are probabilistic, meaning that they emit photons at random times with low probability. This limits their scalability and efficiency. To solve this problem, scientists have been working on deterministic single photon sources, which can emit photons on demand with high probability and purity. One promising approach is to use solid-state quantum emitters, such as quantum dots or color centers in diamond. These emitters can be coupled to optical cavities or waveguides to enhance their emission rate and directivity. By applying electrical or optical pulses to these emitters, scientists can trigger them to emit single photons with high fidelity and indistinguishability. Another important operation on quantum light is to manipulate its frequency or color. Frequency is one of the most fundamental properties of light and plays a crucial role in many applications. For example, frequency conversion can enable communication between different types of quantum systems or platforms. Frequency modulation can also encode information or implement logic gates on quantum light. To achieve frequency manipulation of quantum light, scientists have been using nonlinear optical processes, such as sum frequency generation or difference frequency generation. These processes involve mixing two or more photons with different frequencies in a nonlinear medium, such as a crystal or a fiber. The output photons have new frequencies that are related to the input frequencies by conservation of energy and momentum. However, most of the nonlinear optical processes are inefficient and noisy for single photons or weak coherent states. To overcome this limitation, scientists have been exploring new ways to enhance the nonlinear interaction of quantum light. One approach is to use integrated photonic circuits, which can confine light in small volumes and increase the interaction length. Another approach is to use atomic ensembles or cold atoms, which can provide strong nonlinearities at low light levels. A third important operation on quantum light is to generate entanglement between multiple photons or modes. Entanglement is a unique feature of quantum mechanics that allows two or more particles to share a quantum state. Entanglement can enable tasks that are impossible or hard to achieve with classical resources, such as superdense coding or teleportation. To generate entanglement of quantum light, scientists have been using various methods and sources. One method is to use spontaneous parametric downconversion, SPDC, which is a nonlinear optical process that converts one photon into two photons with correlated properties. SPDC can produce entangled photon pairs or multi-photon states with different degrees of freedom, such as polarization or time bend. Another method is to use linear optical elements, such as beam splitters or phase shifters. These elements can transform the input states of light into output states with different superpositions or correlations. By combining these elements with single photon sources and detectors, scientists can create entangled states of light with different architectures or topologies. These are just some examples of how scientists are manipulating and controlling light at the quantum level. There are many more methods and devices that are being developed and improved every day. Quantum optics is a vibrant and exciting field that promises to revolutionize science and technology in a new light. That's all for today. Thank you for watching. If you enjoyed this video, please like, share, and subscribe. And don't forget to hit the bell icon to get notified of our next videos. See you next time.